So we'll first introduce the basic formalism PCFGs, and then we'll talk about a crucial algorithm, which is called the CKY algorithm. And this is, again, actually a dynamic programming algorithm, which will allow us to use PCFGs to parse sentences. So here is a PCFG, and you'll see that it basically looks exactly the same as a context-free grammar, but we now have probabilities assigned to each rule in the grammar. So here I have a set of context-free rules, and we'll again assume that S is the start symbol under the context-free grammar. But now in red I've shown a probability for each rule. So S goes to NP VP, for example, has probability 1. VP goes to VI, has probability 0.4, and so on and so on. These probabilities have one critical property, which is the following. If I take any non-terminal in the grammar, so let's take VP for example, there are a number of possible ways of expanding that non-terminal. So VP can be expanded in 3 different ways here. It can be written as VI, or VTNP, or VPPP. 3 possibilities. And notice that the 3 probabilities associated with these 3 different options sum to 1. So 0.4 plus 0.4 plus 0.2 is equal to 1. And this is the key constraint on the probabilities in a PCFG. If I look at any non-terminal, we must have these probabilities summing to 1. Here's another example. It's NP. Can rewrite in 2 different ways, either as a determiner followed by a noun, or a noun phrase followed by a prepositional phrase. These 2 probabilities sum to 1. So these probabilities have a clear interpretation, which is the following. They are the conditional probability of, conditioned on a particular non-terminal. We have multiple different ways of rewriting that non-terminal. We now have a distribution over those different options, over those different ways of rewriting that particular non-terminal. Okay. So then we can do the following. So let me just illustrate this definition down here, or this text down here. Let's take a particular parse tree under this grammar, very simple one. So notice that every one of the rules I'm using here is in this grammar. So that's a valid parse tree under the underlying context-free grammar. We're now going to assign a probability to this entire parse tree, which is simply a product of probabilities for these different rules. So if I look at the first rule, S goes to NP VP, that has probability 1. And then NP goes to determiner NN, that has probability 0.3. Determiner goes to the, has probability 1.0. And so to calculate the probability of an entire tree, I just multiply together the probabilities for the different rules. So VP goes to VI, has probability 0.4, and VI goes to sleeps, has probability 1. Okay, so that's the final expression for the probability of this particular parse tree. So more abstractly, if a tree has rules, alpha 1 goes to beta 1, alpha 2 goes to beta 2, up to alpha n goes to beta n, this is the left-hand side, this is a non-terminal for each rule, this is the sequence of non-terminals on the right-hand side, then the probability for the tree is the product of these parameters. So I write Q, so for example, Q of VP goes to VT and P is equal to 0.4 in this grammar. So each rule has a parameter, Q of that rule, which is some probability. The probability for an entire tree is the product of these Q terms, just as I illustrated here. So one useful intuition behind PCFGs is the following. We can now think of top-down stochastic processes under which we can sample parse trees or derivations under a PCFG. So recall that S is our start symbol, so a derivation always starts with S. Now at each point in the derivation, I'm again going to pick the leftmost non-terminal in my current derivation, S in this case, and I'm going to use some rule to expand that symbol. So let's say I pick this rule here, S goes to NP-VP. And we can think of this as a probabilistic process where we choose this rule with the probability under the grammar. So in fact, there's only one way of expanding S as NP-VP, and so with probability 1, we're always going to rewrite this as NP-VP under the grammar I showed you on the previous slide. Next step in the process, we take the leftmost non-terminal again, NP, and you can again think of a stochastic process where we choose the rule expanding NP from the different possibilities using the distribution under the grammar. So in this case, we might choose NP goes to determine NN, so notice that NP is now replaced by these two words, sorry, these two symbols, and that has probability 0.3. Now we pick DT, we choose a rule from the grammar. This actually rewrites as though with probability 1, and so on and so on. So this probabilistic top-down process is going to terminate when I end up with a sequence of words. So now at this point I have no non-terminals left. The parse tree underlying this, of course, is S goes to NP-VP. It's going to be something like this. And the probability is going to be the product of these different terms. So you can, in fact, once you have a probabilistic context-free grammar, sample derivations from that context-free grammar in this sort of top-down process. So you can use a probabilistic context-free grammar to generate parse trees. Okay, so some crucial properties of PCFGs. Firstly, as we've said, they assign a probability to every possible parse tree allowed by the underlying context-free grammar. So to calculate the probability of a parse tree, I just look at the rules in that parse tree and multiply together the different probabilities. Most crucially for our purposes, we have the following. So say I have a sentence S. So let's say, for example, it's the dog saw the man with the telescope. So this is our sentence S. This sentence may have several different parse trees under the underlying context-free grammar. So let's say we have a couple of different parse trees, which I'll just sketch here under the CFG. And as we said, this is the ambiguity problem. The problem is that our grammar is generating more than one parse tree. So I'll call this entire set of parse trees T of S. Okay, so T of S is the set of possible parse trees for this input sentence. Now critically, now I have probabilities on these rules in the grammar, I can calculate the probability of each of these parse trees. So I might, for example, calculate the probability of this one as 0.01, and maybe this one is 0.00057. And so now I get this additional information where each parse tree in the grammar, each parse tree for this particular sentence has a different probability, and that gives a ranking on the different parse trees in terms of their probability or likelihood. And so given this ranking, I can, for example, simply output from my model or from my parser the highest probability tree under the model. So I now have a way of choosing between different parse trees. And so the parsing methods we'll look at will first somehow learn the parameters of a PCFG from data, and then given a new sentence, they will search for the parse tree that has the highest probability under the grammar. And if the PCFG does a good job of modeling the probability of different possible parse trees, we'll end up with an accurate parser that more often than not resolves the ambiguities that I just described to you in the previous lecture. So one last definition: if we have the sentence S, then the most likely parse tree for that sentence is, if we look at all trees in that set T of S, remember T of S is the set of possible parse trees for S, we now just choose the highest probability tree under our PCFG.
Reach for
So the next thing we should discuss is how we can actually learn a PCFG from data. And as I described earlier in the course, we have resources available called tree banks, which are extremely useful for this purpose. So an early and very famous example of a tree bank is the Penn Wall Street Journal tree bank. And tree banks consist of sentences. Here we have a 30-word sentence, together with their underlying parse tree. And these parse trees are actually annotated by hand. So for example, in the case of the Penn WSJ tree bank, a group of people in the early 90s at University of Pennsylvania got together and came up with a set of conventions based on linguistic theory for the form of these structures, and went through and annotated 50,000 sentences. That's close to 1 million words of data. So we actually have example parse trees from which we can learn the rules and parameters of a PCFG. The Penn WSGA tree bank was one of the earliest examples, but by now we actually have many different resources in many different languages of this form. So once we have a tree bank, learning a PCFG is actually extremely straightforward, almost trivial. So there are two things we really need to learn. One is the set of underlying rules in the context-free grammar, and the probabilistic context-free grammar. So we might, for example, learn a few rules like this. And the other thing we need to learn is parameters associated with these rules, for example, 1.0, 0.6, and so on. In terms of the rules in the PCFG that we learn, we simply take all rules seen in the tree bank. So learning, quotes, learning the context-free grammar is simply a matter of reading off the rules in the tree bank, reading off the context-free rules. How do we estimate the parameters? So remember, Q of some rule alpha goes to beta is the probability associated with that rule. We're again going to make use of maximum likelihood estimates, which again have a very simple and intuitive form. And so to estimate the parameter for some rule, alpha goes to beta, we take a ratio. So on the denominator we have the number of times we've seen alpha, and on the numerator we have the number of times we've seen the entire rule. So for example, QML of VP goes to VT NP would simply be count of VP goes to VTNP divided by count of VP, where these counts are taken very directly from the example trees in the tree bank. There are various guarantees for these kinds of estimates. This is one important one. So if the data we're looking at, if the tree bank is actually generated by some underlying PCFG, you can show that as the training data size gets larger and larger, these parameter estimates will get closer and closer to the true underlying probabilities in the PCFG generating the data. And that leads fairly directly to a property that the distribution over entire parse trees defined by our PCFG that we learn converges to the correct underlying distribution under the PCFG, which is generating our training data. Bottom line though, given a tree bank, it's very easy to learn a PCFG. We simply read off the rules from the tree bank, and then we calculate these maximum likelihood estimates, which amounts essentially just to counting the number of times we've seen non-terminals and counting the number of times we've seen entire rules. So I just want to talk about one final technical property of PCFGs. This goes back to work by Booth and Thompson from the early 70s. So if we step back and think about what we've done, it's really rather remarkable. So if we take a given CFG, there will be some set of well-formed parse trees under that CFG. So we have some set of parse trees. These are quite complex structures. And in fact, for many CFGs, this set will be infinite. So actually, for the CFG I showed you earlier, there are actually an infinite set of possible trees. We now have a way of calculating a probability for each tree under the CFG. So for example, this might be 0.01, I have 0.00057, 0.004, and so on and so on. And we've done this by simply assigning a probability to every rule in the CFG, and then for a given tree, we just multiply together the rule probabilities within that tree to get this probability. So for this to define a correct distribution over possible parse trees, these probabilities have to sum to 1. So we're attempting to define a distribution over an infinite set and an infinite set of quite complex structures. So Booth and Thompson give conditions on the rule probabilities under which we get a proper distribution over trees. The first one is exactly what I showed you earlier, and it's by far the most important. And that is that if we take any non-terminal, for example VP, and we look at all of the rules with that non-terminal on the left-hand side, for example, we might have the following, then these rule probabilities have to sum to 1. Okay, so this would be valid, for example. That's the first condition. And that's really the only one you really need to worry about. I'll just briefly mention, though, that there are some other conditions which are rather technical, and we'll go over them very quickly, although they are somewhat interesting. So let me give you an example of a grammar which satisfies this first condition, but actually does not define a distribution over possible trees. So the rules in this grammar are very simple. S goes to SS, or S goes to A. And so we'll generate parse trees like this, or this one right here, and so on. And in fact, you can see there are an infinite set of possible parse trees under this grammar. And let's say I choose probability 1 for this rule, probability 0 for this rule. So this satisfies the condition that the rule probabilities sum to 1, but actually for any finite tree, this is going to get probability 0 because it has S goes to A in it. This is going to get probability 0 because it has S goes to A in it, and so on. So actually it's going to assign probability 0 to any finite tree, and it will fail to define a distribution over possible trees. Okay, so that's a simple example of a grammar that satisfies condition 1 but is ill-formed in some sense. A second example, which I'll just very briefly mention, is a little bit more surprising. You can actually show that under certain settings for these rule parameters, so if I say 0.6 for this and 0.4 for this, you can actually show that this grammar also fails to define a well-formed distribution over trees. You can show that the sum of probabilities for the set of finite sized trees actually sums to less than 1 for this particular case. And intuitively what's going here is the grammar is splitting too quickly, and it has probability less than 1 of actually producing a finite length parse tree. Okay, but I just wanted to mention that very briefly. It's sort of curious. In practice, this is never really a practical concern, but it's just worth having at the back of your mind. Next, let's talk about lexicalized probabilistic context-free grammars. I'll give some basic definitions. Okay, so firstly, to recap, let's remind ourselves of context-free grammars in Chomsky normal form. So a CFG in Chomsky normal form consists of the following. N is a set of non-terminal symbols in the grammar. Sigma is a set of terminal symbols or words. We have S, which is a distinguished start symbol, which always occurs at the root of the tree. And then finally we have a set of rules R, and each rule in R must take one of two different forms. So it either has the form x goes to y1, y2, where all three elements x, y1, and y2 are non-terminal. So an example would be S goes to NP, VP. Or it consists of x goes to y, where x is a non-terminal and y is a word. So for example, dt goes to there. And we saw that given a PCFG in Chomsky normal form, we can use dynamic programming to find the highest probability paths in order cubic time in the length of the sentence. So n is the length of the sentence, and cubic time in the number of non-terminals in the grammar. So here's a definition of lexicalized context-free grammars in Chomsky normal form, which is closely related to the definition I gave you on the previous slide. So with a lexicalized CFG, we again assume we have some set of non-terminal symbols, we have a set of terminal symbols, and we have a start symbol. But the rules in the grammar take a slightly different form. So there are three different cases. Let's go through the simplest case first. So this says that we can have a rule where x is a non-terminal and h is a word, where xh rewrites as h. So for example, dt there goes to there is one example of this rule, where x equals dt and h equals there. So these are the rules seen at the very leaves of the tree, where a part of speech with some lexical item simply rewrites as that lexical item. Now let's look at these two remaining cases. Let's look at this one first. This says I can take any three non-terminals, x, y1, y2, and any two words, h and w, and I can have a lexicalized rule where xh rewrites as y1h, y2w. Let me give you an example of such a rule. We could, for example, have VP soar goes to VT soar NP dog. Now critically, I'm going to subscript these arrows. This has a 1 here to specify which of the two children is the head of this rule. So because soar is on the left-hand side of the rule and soar is here on the first non-terminal, I subscript the arrow 1 to say that that's where this head word came from, that this is the head of the rule. So in this particular example, we have x equals VP, y1 is equal to VT, y2 is equal to NP, h is equal to soar, and w is equal to dog. This case is similar. So let me give an example of this rule. This, for example, could be S soar goes to 2 NP man VP soar. Notice in this case the head word comes from the second child, and that's why the arrow is annotated in this way. So this annotation on the arrows is sort of a pesky detail, but it's important. And it's important because it avoids ambiguities. If, for example, I have NP dog goes to NN dog, very unlikely, but possible, where the H is equal to dog and W is equal to dog. We're just going to be careful to specify which of these two children the head word came from. So here's an example of a lexicalized context-free grammar in this Chomsky normal form. And let me show you a parse tree under this. So we have S soar goes to, for example, np man vp sor, and we'll just mark this to say that this is where the head came from, this is the head of the phrase, and then np man could go to dt there, nn man, for example. So I've used this rule, and now I'm using this rule. Again, let's mark the head. And then we have there, and we could go on and on. So we have derivations with these lexicalized context-free grammars, which look very similar to derivations under regular context-free grammars. We just have head words associated with each of these non-terminals in the tree. So we will introduce parameters or probabilities in these lexicalized PCFGs. It's important to emphasize the similarities and differences from regular PCFGs. So in a regular PCFG, we saw parameters like the following. For example, Q of S goes to NP-VP. This is basically the conditional probability. Given that I have an S, there are going to be multiple ways of rewriting that S. NP-VP is going to be one of them. And this is going to be the probability that we choose this as opposed to all those other alternatives. We have parameters in lexicalized PCFGs, which again are associated with entire rules. So here's an example parameter. And now this parameter is for the rule S sor goes to NP man VP sor. So this again is going to have an interpretation as a conditional probability. In this case, the interpretation is, given that I have S sor on the left-hand side of a rule, there are many, many different possibilities. One is to choose the second non-terminal as the head, and to choose NP man VP sor as the two children. And there are going to be many, many other possibilities. So there are definite similarities between these two models. In fact, technically speaking, a lexicalized PCFG really is just a special case of PCFG. But qualitatively, something has really changed, which is that we've gone from a relatively small number of parameters in this original model to a very, very large number of parameters. We have one parameter for every possible lexicalized rule. And so we're going to have to be very careful in how we estimate the parameters of these models. But we'll see that the smoothing techniques you saw for language modeling in the very first segment of this course can be applied very, very directly to this problem. Next, let's talk a little bit about parsing with lexicalized CFGs. I don't want to go into tremendous detail about parsing algorithms for lexicalized PCFGs, but I want to give you a sketch here. The main point being that you can use a very, very similar dynamic programming algorithm to the dynamic programming algorithm we saw for regular PCFGs. So the new form of grammar I've just shown you is very similar to a Chomsky normal form CFG. But whereas before we had rules like S goes to NP-VP, so there are order n cubed possible rules where n is the number of non-terminals, so I have n times n times n. In this new grammar I have things like S sor goes to NP dog VP sor. And so if I think of the number of choices, well, I have three non-terminals here, S, NP, and VP, so I have n cubed choices there. And also in each rule I have two words, the head word sor and the modifier word dog. And so I'm going to have sigma squared. And so there are many, many possible rules. Okay, so I've gone from a grammar with order n cubed rules to a grammar with this many rules. So naively, you could just pick up the dynamic programming algorithm we saw for probabilistic context-free grammars and apply it to this new grammar. These rules are really just like regular context-free rules. We can just treat these as non-terminals. We just have a much larger set of non-terminals than we had before. But if you do this naively, you'll end up with the following running time. Remember, before we had order n cubed times number of non-terminals cubed. as the runtime for dynamic programming. This is our new runtime, and we have sigma squared coming in here. This is a terrible idea because the vocabulary size can be huge. Sigma could easily be on the order of hundreds, or much more likely thousands, or even tens of thousands. But there's a simple observation which gives us at least a plausibly efficient algorithm. If I have a particular sentence, like the dog saw the cat, I can immediately discard rules such as the following. So S questioned goes to NP dog, BP questioned. I can immediately discard this rule because it has a word questioned in one of these non-terminals, which is seen nowhere in the sentence. So we know that rule can never be used in parsing this sentence. And so we can actually restrict ourselves to a much smaller set of rules, where we now have order n squared times n cubed, because, again, we have capital N choices for each of these three non-terminals. And then these two words, rather than being drawn from the full vocabulary, have to be drawn from one of the n words in the sentence. Okay, so we end up with a much smaller set of rules just by restricting the grammar in this very simple way. And this is actually going to lead to a runtime of order n to the fifth times n cubed. Where does this come from? Well, we have order n cubed. It's a dependence of the dynamic programming algorithm on the sentence length. And then we have to multiply in the number of non-terminals or rules in the grammar. And so this is where we get order n cubed times n squared. It's the number of possible rules, and so this is the runtime we get.